And the temporary host, and we are recording, including a fantastic typing noise.
I guess you don't really see the slides in a big window, right?
Yeah, they're taking up a pretty small portion of your screen.
Yeah, that's a little bit annoying. I thought it would only...
Definitely better, thanks.
Okay.
So, Miriam, do we have a couple of people who volunteered to help take notes in the pad, or do we want to try and arm twist for that now?
Yes, my approach was to just ask everybody to share their notes with us later on. But you know, if people want to have common note taking in the notepad, that's probably even easier. So I don't know. Should we try to find one lead note taker? Anybody volunteering?
So I think it would be more helpful to just take collaborative notes in the Etherpad, because if we don't actively engage in the note taking, it probably won't happen, is my experience. Or, you know, trying to pull everybody's individual notes in different formats. So that's my suggestion.
So I don't think we need detailed minutes for this meeting, and we will have an IB report published afterwards at some point.
Yeah, so I think the good thing to put in the Etherpad as notes is stuff that would go in that report.
Yeah.
So, or at least a reminder to somebody to go and check this bit of recording.
So I guess you have an eye on it, Stephen?
Sure, but it's good if other people do that too. I'm not good at taking notes because I always think I'll remember stuff and then forget.
Is there a link to the Etherpad?
It's in the chat. I'll post it there again.
Okay, yeah, the chat history is
sure
not a thing.
Okay, but given it's 5 minutes past, I would suggest that we just start. I think people have, like, most people are here. I don't hear the joining noise anymore, so let's start. So welcome everybody to the IAB workshop on COVID-19 network impacts. This is the first session we have today. We have 2 more sessions on Wednesday and Friday. Thanks everybody for joining. And we will go right on the next slide. Yes, so this is also part of the IETF. So the node wall applies here. However, you know, if you have something to share which needs another framework, you can indicate that and we can see what we can do. But otherwise, you should assume the node wall applies. And you can see this also as a contribution to the IETF. Logistics, we have a webpage which has some information about the workshop, which you might have seen because you might have submitted something. It has also all the papers on there that we have accepted. Thank you everybody for submitting a paper. We received a few more papers than on the which have not been published or then are published on the webpage, because we only published like real full position papers on there. If that was just like a short statement of interest or whatever, we didn't publish it. But I think the papers we got cover a really nice broad spectrum of input, and we're happy to have you all here. We also created a GitHub repo. The GitHub repo currently has mainly the slides from today. It also has already an MD file for the report. So if you guys already want to put some notes there or start working on the report, that's also helpful. Then we're today here on WebEx. We will use the same WebEx session on Wednesday and Friday. The session is currently recorded. The intention is to publish the session, the recordings later, and also use them potentially for note-taking, looking up stuff. So if you have any concerns, if you want to share something that should not be published, we can actually stop the recording. You have to indicate that. But otherwise, we would just assume that we can publish the recordings later if you're not indicating otherwise. You should turn on your video when you're speaking or presenting. Not sure if you want to keep on your video otherwise the whole time. We have a lot of people in here. I don't think should be a network issue if the tools are smart enough by now, but like feel free to turn it off anytime. Make sure you're muted when you're not speaking. That can be messy otherwise. And for the queue, we will try to use the plus Q minus Q scheme in the chat. So Yari is helping me watching the chat for the queue, and I hope we can manage this well. The goal is to have a very interactive discussion here. But we are too many people to just speak, I think, so we need the scheme. And then on here is also the link to the Etherpad that Stephen already published in the chat. Somebody is not muted and making noise. So that person didn't listen? Well, thanks. So Etherpad, we have the Etherpad for taking notes, but if you can also put your name and affiliation there, then we have a little bit of record who was here. That would be very helpful. Any questions on the logistics so far? Okay, then let's talk about why we're here. So the scope of this workshop is really to talk about what we have seen in the crisis that's actually still ongoing, but mainly also in the first peak of the crisis, and what was the impact on networking. I think we have all seen many reports how quickly the traffic went up in March and April, because everybody moved to home, work from home, and there was a big shift in also different applications that were used, especially video conferencing, media applications had a big increase. And all over, we saw that actually things worked well. We know that some operators managed to upgrade their capacity quickly. There have been like some small hiccups. We also saw in the EU, there was a request, for example, for Netflix to actually reduce their video rate and lower the traffic load there and these kind of things. So this workshop is really to figure out a little bit more what happened, what have we learned, and what do we need to improve in future from a networks operator and service provider point of view, but also from an architecture point of view. What's in the technology that maybe needs changes, or what's set up in a way to survive those crises very well that we should make sure we maintain. So it's really about figuring out what had happened, figuring out what was behind the scene about network management and capacity extensions, and also, what are the general impacts of these traffic shifts to our architecture and potentially in any kind of future effects. And a little bit about these 3 points, we also set up our agenda. So our session today will focus on measurements and observations. We have a bunch of a few slides presentation from people who send us papers about measurements. This is really to get everybody on the same page, get some knowledge about what happened, get some data, and have a discussion about this. The session on Wednesday will focus more on operational issues. So really, what did the operators do? What was their experience? And what can we learn from it? And then on Friday, we will be a little more future looking, And we also have hopefully some time for other topics people want to discuss that didn't find a place in the earlier sessions. We have Colin on the queue.
Thanks. I was just thinking at the end of Monday and Wednesday, can we just reserve a little bit of time to stop our normal discussion and just make sure that we sort of outline what we want to talk about the next day so that we can sort of guide those agendas a little bit more?
Yeah, that's a really good idea.
Okay, thanks.
Okay, any more questions on the scope and the plan for the meeting for the next days? Okay, then let's start with today's topic. So I looked at all the measurement papers, which you can find on the IAB webpage. I also looked at the slides I received already, and the overall observations isn't that surprising, right? We had like this huge increase in traffic in March and April. We have observed changes in traffic pattern because we have different kind of applications people are using because of the different way they work and they live. We have especially this very strong increase in video conferencing. We have seen, based on measurements, we can also see that there have been reactions from operators upgrading their capacity more quickly than they would usually do. And we had got also some measurement papers showing that there are still problems about last mile congestion and latency in some networks, depending on actually how the infrastructure is set up. So this is just like the very high level view. And we kind of dive today a little bit more into the data and looking at the details and figuring out, did we actually measure the right thing? Do we know everything we know? Or did we miss anything here? And as such, we also have these presentations, which I tried to structure a little bit in this way. And there's Kirsty in the queue.
Hi, thank you. Yeah, I just wanted to, sorry, you mentioned if there's anything you missed in the high-level observations, just in terms of a shift on traffic pattern. And I think we should really acknowledge the shift in cyber attacks and the security aspect of what we saw in terms of the shift in traffic pattern. So I just wanted to mention that as a high-level observation before we go into more detail here. Thanks.
Thank you. That's a nice contribution. We don't have a measurement paper about this, though, but that's definitely something we can further discuss. Okay, so on the measurement papers, I considered the order we want to go through this, and there are different ways to do that, but that's the order I choose. I would like to start with Oliver on a paper which he called the lockdown effect, because they have various measurements from different kind of networks, and this shows a really nice high-level overview, getting some data at the observations I just stated. Then we have this little block where we go a little bit more into specific traffic patterns in campus networks and mobile networks. And then we have papers looking more at interconnects at different points. And then at the end, we talk about this last mile congestion problem that I mentioned. So that's the plan. Any kind of agenda bashing for today? I can also quickly flip on the next slide. So there's a slide with potential questions we want to address later on. Of course, your own questions can go here as well. You can look at the slides in GitHub if you want to double check this. But let's look at the presentations first. And with that, we can start with Oliver. And I will try to find the slides. Should be this slide set. And I increase this again a little bit for you. Oliver, are you there and ready?
All right, thanks, Mirja. Then, so thanks for the introduction. My name is Oliver Holfeld, and on behalf of all the authors, I'm going to present our paper on the lockdown effect. So what we intended to do was we wanted to take a very broad perspective on what is actually happening in the internet when the entire world shifts their behavior. So we have a couple of vantage points, an ISP, internet exchange point, and an educational network. And we want to look at all of this broad set of networks. Wow, how did they actually cope with the traffic change and what was actually happening in terms of measurable observations? So next slide, please. So we have a lot of vantage points, so a lot of data to crunch. That means we have a lot of data crunchers that are involved in this project and looking at the different perspectives. So next slide, please. So what kind of vantage points do we actually have? So we're looking at 3 internet exchange points. So one big internet exchange point in Central Europe, one in Southern Europe, and one internet exchange point in the US East Coast. So that's kind of the core networking perspective where a lot of the networks meet. Then we are also looking at a big internet service provider, and here to get the residential customer perspective. So all the DSL customers that have now have to work from home. And then we're also looking at a big educational network in the Madrid region that interconnects more than 16 different research institutions, students, faculty members, and so on. So next slide to give you a view on how this traffic evolution is kind of developing. Here you see a plot that starts in January last year, and it goes up until the end of June this year. And what you see here on the left portion of the plot is more like the general increase in traffic that we have. So as time progresses, we're more utilizing our networks. However, when the initial responses and lockdowns were announced, so this is the part in the plot where it goes from like the white shaded background to the gray shaded background. So that's in March this year, when the governments imposed lockdown restrictions, we have a big jump in traffic in the order of 20 to 30%. And this is just because people change their behavior and because of changes in life. So that's a big additional set of traffic that these networks needed to handle. So this is what we see at this internet service provider. Now we have a couple of more vantage points. So if you go to the next slide, we see how this looks like for the internet exchange point. And here we see exactly the same behavior for every of the 3 internet exchange points that we're looking at. So we have a more or less gradual increase in the traffic evolution. And then once these lockdowns were announced and the restrictions were imposed, then we have a big increase in traffic in the order of 20 to 30% in every vantage point that we're looking at. If you go to the next slide, then we can have a look in how this looks from the perspective of a mobile operator. And here, as we would expect, we see a slightly different picture. So once the lockdowns are in place, the traffic is slightly decreasing. So that's the general observations that we can see here in terms of how the traffic level is rising. So next slide, please. What are the takeaways that we can take from all of these measurements that we did? So people's life changes, and this leads to the advent of new traffic patterns. And most notably, what we observe, and this is in line with like many of the other works and operators' perspectives that have been shared, meanwhile, is that the difference between workday and weekends vanishes. So all the work days becomes a bit more like weekends. So the difference here kind of vanishes, the traffic composition changes. And in terms of traffic composition, here we see shifts. So for example, all the applications that we use for remote work, education, VPN, video conferencing, you mentioned it in the beginning, all of these applications see an increase in traffic. I showed you in the beginning the plot of the general evolution of the traffic increase, and this is what is mostly reported, and you mentioned it in the beginning, this is what we mostly talk about, networks increase in traffic. This is, however, not the case for all the networks. So for example, if you look at educational networks, if you send people at home, they cannot use the networks anymore. Oh, well, they use it for different kind of services, so they need now streaming, meaning that the traffic symmetry and the in and out ratios, they completely change. And then, of course, if students are sent away from the campuses, then these campus networks are not utilized anymore. So they kind of see a decrease in traffic. And for the educational networks here that we looked into, we saw an up to 55% decrease in traffic. The other thing is that we see here is that most of the people, when they look into internet traffic, they look at hypergiants, so the big CDNs and cloud providers and so on. What we notice is that, however, only focusing on these hypergiants is not sufficient, because we saw a lot of increase in these non-hypergiant networks. But in general, what we find here is that once the human patterns and their behavior changes, this is directly reflected in internet traffic patterns that operators need to account for. So next slide, please. So what we saw here is that if we just look into the traffic volume, then we saw an increase of about 15 to 30% with just a few days only. So that happened rather quickly. And if you now consider that networks usually provision for about a 30% increase per year, this is pretty substantial. In terms of like, how did the networks cope with that? Mostly pretty well, because they had sufficient idle capacity provisioned. But there's another effect that happened in here, is that the impact on the peak traffic was rather limited. So most of the traffic shift, they occurred in non-peak hours, which means that the valleys get filled, but the increase in the traffic peaks is not that substantial as the actual shift in the traffic. The other observations that we made here was, when we looked into port capacities and how did networks deal with provisioning their links, was that most of the networks actually reacted rather quickly to the additional need for capacity, and they were very quick in provisioning additional capacity. So for example, here the Central European IXP reports a capacity increase of about 1.5 terabits here. So what can we take away from this is that networks could deal with this sudden increase in traffic and these shifts in demand pretty good if they had sufficient idle capacity provision, and they had like a very quick reaction times in terms of like provisioning new links and adding capacity. So this is why for like these kind of bigger networks that we looked into, the impact of the pandemic was measurable, but it didn't really hit these networks. So with that, I'm at the end. Thank you, and I think we go to the next presentation before we jump into questions.
We can have some questions if people have clarifying questions or whatever. Next presentation will look a little bit more deeply into especially campus networks, so that fits here directly. But we can also see if somebody has a question or already wants to comment on something.
Yeah, I have a quick question on, I think, the second slide with graphs. No slide numbers, so we but yeah, the next one. Yeah, so there's a downturn on the right hand side there. There's one line that returns back down to the normal, if you like, or the status quo. Okay, what was happening there?
With that, I would like to hand over to Chris or someone from the DKIC.
Yeah, so thanks, Ollie. Unfortunately, I'm currently not able to view the exact graph. So which one is it, Ollie? So I have in my browser, I don't see the shared presentation. So
that's the second plot with the second slide with the IXP plots. And here it's, so the dip that you're referring to is the South European IXP.
So let's move on for now. Maybe you can check this out and let us know later on. I guess it's also actually, yeah. Jenben is in the queue, yes.
On the page, on the last page, I have a quick question. Okay, so here mentioned that the capacity is can be increased well because of the planning in advance. But you know that in the process of the COVID-19, because I think the capacity may be not a very big problem, but you know, we know that the experience of the users may be not the same as usual. I'm not sure if there are some data to evaluate the experience of the user in this field.
Yeah, so we do have more presentations talking about some places like Japan where there was actually much more congestion and higher latency. So let's maybe keep that for later discussion.
Okay, thanks.
Okay, I would just in this case move on, and we have Martino next. Let me find those slides.
Hello.
Hello, we can hear you. There you go.
Hello. Hello, everybody. First of all, thank you for all the organizers for the nice initiative. I will present something about our paper about campus traffic during the pandemic. As also Oliver was mentioning, the COVID pandemic had an impact also on the campus networks, and very often we see a decrease in traffic, but not always. And in our network in Politecnico di Torino, we see an increase of traffic due to some specific situations. If you go to the next slide. Okay. Thank you. Yes, in our paper we collected some data from our campus, Politecnico di Torino, some passive data using a network probe running a passive meter called T-Stat that we developed here in Politecnico di Torino, and we compared what happens in our university with respect to other large universities in Italy. Here on these graphs we see how the traffic pattern changed from before the lockdown and during the lockdown. Here we have the daily pattern. On the top y-axis we see the incoming traffic pattern, while on the bottom y-axis we see the outgoing traffic pattern. If we focus on the incoming traffic, this is mainly what people do while browsing. And we see that in all the three universities, we see a very large decrease of incoming traffic due to the lockdown, because people are no longer there in the university. They do not browse, they do not download content. Instead, if you look at the outgoing traffic, which is basically the traffic served by the servers of the university, we see that in Politecnico di Milano and Università di Torino, the outgoing traffic is almost remain the same. But in Politecnico di Torino, which is the left image, we see that the outgoing traffic really exploded. This is the red line. And the reason is because Politecnico adopted an in-house teaching infrastructure. So basically all the lectures are distributed by servers inside Politecnico di Torino rather on the cloud. And this makes the outgoing traffic to explode. In the next slide, we have some details about that. In general, we observed different traffic modifications due to the COVID pandemic. First of all, we can mention that we noticed a large increase in remote access, so in VPNs and remote desktop connection for the internal resources of our university, because professors, but also technicians and administrative staff were forced to connect from outside. We also testified a large increase in the use of Microsoft Teams, because in our university, Microsoft Teams is used by faculties to communicate with students, for administrative staff, for storage, and these things. And finally, the most important traffic change was due to, as I said, to the remote learning infrastructure that we set up in Politecnico, which is based on BBB, Big Blue Button, which is an open source application for remote teaching, which is based on WebRTC. And in turn, it uses RTP traffic to distribute the live lectures to the students. This had a large impact on the campus traffic. If you see the bottom left image, we had like 600 virtual classrooms per day and 15,000 users connected every day. Also, what is important here is that these traffic changes are persistent, so they are not only during the first days of the lockdown, but they lasted all the lockdown long. So if you see the figure here in the bottom right, this is the incoming outgoing traffic pattern. We see that during the lockdown, the outgoing traffic really exploded while the incoming traffic dropped. But this is persistent. So also now during the second semester, we have a huge amount of outgoing traffic due to remote lectures. This traffic even increased because we have all the new students, because all the classrooms are now working remotely, and so we have like 2 gigabit per second of outgoing, mainly RTP traffic. If we go to the next slide, we can also see how this modification created some different traffic pattern in terms of daily and hourly pattern. So here we have a breakdown of the traffic due to remote teaching. So outgoing traffic, we have live classrooms, which are based on RTP traffic. They are live, so this is UDP RTP, and they happen only during the weeks. And during the weeks from 8:30 to 7 p.m., we can observe up to half gigabit per second of outgoing traffic due to virtual classrooms. But there is also a large traffic due to the on-demand content that students download, because students can for sure download also the classrooms offline, for example, during the weekend. In fact, we noticed that during Saturday and Sunday, we have almost half gigabit per second of downloads of teaching material. And this is huge because before the lockdown, we didn't observe such a large traffic during the weekend. And so also this is a very hard modification. This traffic pattern also has another characteristic, because lectures are scheduled to start every 90 minutes. And so every 90 minutes, the students connect and start watching the classroom, and this triggers new TCP and UDP flows that are born coordinately. Even if the traffic in terms of packet per second is not doesn't have these peaks, the number of new TCP and UDP flows exhibit a great peak during the beginning of these of the classrooms. And this can be a problem, for example, for firewalls, for some middle boxes, for passive meters, for all these kind of network equipments that need to have a per flow state inside. So this can be a problem for some network equipments. If we go on the next slide, we can finally study the performance that students enjoyed while using our teaching facilities during the lockdown. Here we first focus on the speed, the download speed of the teaching material, which happens over HTTPS, over TCP. There is some difference across operators because we noticed that fixed and fiber operators are typically much faster than mobile and low-cost operators. This is the figure here on the left, on the top. We see that, for example, Fastweb was much faster than Free Mobile, which is Iliad, which is a mobile operator. Also, we noticed that at some point, all the traffic from Italian students going from Italy to our university was routed to the France and then coming back to Politecnico di Torino. And this was a clear performance penalty that students were enjoying. And on the contrary, we didn't notice great differences across Italian regions. Here, this is the graph on the bottom left. The throughput, yes, there are some variability of the throughput between regions, but not as much as we expected. And this was rather interesting because also in Italy, there is a large debate about the digital divide, for example, of rural areas, of islands. In Italy, we have Sardinia and Sicily. There is a huge debate about if the internet is lower or faster in these islands. And actually, we did not measure such a different performance across regions. And finally, we can say something about live classrooms, which happen over RTP in UDP. Since this is not a batch download, it has a fixed bitrate at which the content is generated by the teacher. And we didn't notice any problem due to the network during the lockdown, actually. Also because the bitrate is rather low. The video is very seldom above 200 kilobits per second because we set up a low video bitrate to avoid congestion, and also audio is typically at 40 kilobits per second. So this almost never saturated the network of the students, and we didn't, no big problems were reported by the students during the lockdown. Yes, this was the last slide. In general, yes, we can say that from the campus point of view, it has been a large effort to set up this teaching infrastructure. This clearly stressed the campus network to have such a large amount of outgoing traffic, which kind of really modified the pattern rather than before the lockdown. Before the lockdown, we had incoming traffic and not much outgoing traffic. Now we have almost all outgoing traffic. But in general, the network managed to carry packets. And that's all. Thank you.
Thank you very much for sharing, especially this last slide, because there's a lot of discussion already ongoing about how to measure user experience. Before we take Oliver, I have a quick question. So on the previous slide, you talked about that the number of TCP connections would challenge like firewalls and these kind of things. So did you see any outages there, and did you have to upgrade those firewalls, or did you do anything there?
Regarding the firewall, I don't know if they had problems, the technicians, but for our passive probe that is running TSTAT, which is a custom software, a custom passive meter, at some point we had to increase the number of cores because it is a multi-core, multi-threaded. We had 2 cores, we had to upgrade it to 4 cores because the traffic increased too much. So, but I'm pretty sure that the network administrator had some other problem.
Okay, thank you. So then we have Oliver.
Yeah, I have a question regarding slide number 2, where you compare the basically the incoming versus the outgoing traffic before and after the lockdown. So, and especially for B and C, so basically not the universities where you investigated, I guess, most of the time. So why is there so little difference in the outgoing traffic after the lockdown? So in the lower part of B and C. So why is it almost the same?
Actually, I think that this is because the outgoing traffic is mainly due to the servers, so the teaching portals, and so this pattern didn't change too much, because these are students going there to download slides, to download teaching material, and this maybe has been rather stable. Also, I don't know how is organized the infrastructure of these two universities, how much content is on the cloud and how much content is on premises. So I don't know.
Thanks.
Okay, any more questions? Okay, as I said, we have some discussion ongoing on the chat, so check that out. We will pick that up at the very end, definitely. We move on with looking into mobile networks a little bit more, and we have Andra here, I think. Andra?
Hello.
Yeah, perfect.
Yeah.
Hi. Yes, now we can hear you.
Hi. Great.
Go ahead.
Okay, great. Thanks so much. Yeah, thank you so much for having us today. So I have also Diego Perino joining from Telefonica today. I'm just going to quickly introduce to you a bit of our analysis on the implications of this pandemic on the traffic of a mobile network operator in the UK. So specifically, we're talking about O2 in the UK. So this is joint work with Telefonica Research, University Carlos III of Madrid, and Telefonica in the UK. So specifically, we looked at how the pandemic unfolded in its early weeks within the UK, and how all the government issued measures to actually tackle the pandemic impacted the mobility of the people and implicitly the way in which they actually used the mobile network services. So the period we focused on captures about 10 weeks from the end of February until around mid-May of earlier this year. So within this period, we actually captured a few interesting moments when the World Health Organization declared the coronavirus outbreak a global pandemic, as well as all the follow-up measures the UK government took to impose social distancing, including a nationwide lockdown they declared on the 23rd of March. Next slide, please. So I'm going to start with the takeaways. So in our analysis, we actually found that, in an effort to tackle the pandemic, the UK nationwide mobility decreased by 60% after lockdown compared to the last week of February of 2020. So actually people did stay at home. In the same time, their usage of the mobile network also decreased, and we found a drop of approximately 20% in downlink data traffic after lockdown compared to earlier this year. London in particular, so many of its residents actually relocate elsewhere, showing a 10% drop in residents after lockdown or around lockdown, and a steep decrease in downlink data traffic, especially in central areas of London. However, the pandemic brought voice conversation back in the center of our attention. So people did start calling their relatives more and their close ones more. And we found a surge of about 140% around lockdown compared to February. Next slide, please. So our analysis put together, a rich data set that we actually collected from O2, including a general mobility signaling information data set from devices in the network from the mobility management entity, and radio network performance metrics. So we capture users' mobility only by checking which are the radio towers to which they actually connect. So I must specify that this data is always anonymized and aggregated, and we don't ever access user GPS information. From these data feeds, we complement with third-party information from, for example, the Office for National Statistics, and we derive different mobility patterns at the user level, including the home location of the user and a bunch of mobility metrics. So one of these mobility metrics, for example, is the user gyration, which tells us about the area in which a user moves, only based on the radio towers to which the user actually connects. So next slide, please. So this is where we actually see the evolution in gyration. So based on all this information, we are actually able to observe how the mobility of people changed in the UK in these early weeks of the pandemic. So what you see here is the average variation in gyration compared to the nationwide average in February across our data set of about 16 million users. So we captured the variation from the 24th of February until 30th of March in this plot. So each bar that you see here corresponds to a different day. So what we observe is that although the pandemic was declared in early March, and social distancing was immediately encouraged, the mobility patterns of people did not change immediately. So this actually dropped dramatically once the government actually issued the stay-at-home order later in March. So we note that after the 23rd of March, the gyration drops by at least 60% compared to earlier in February. So the main takeaway here is that the only effective measure to actually convince people to socially distance was actually the countrywide lockdown. Next slide, please. So then we asked ourselves, what did all these changes in mobility actually meant for the mobile network? So to understand the impact on the actual network, we looked here at 6 different indicators, performance indicator, KPIs. So we looked at downlink, uplink data volume, downlink active users, downlink average user throughput, cell resource utilization, and the total number of users in the radio cell. So we only report on the y-axis the delta variations of each of these KPIs compared to the nationwide average in the last week of February of 2020, so prior to the pandemic. So we show here only average values across 1 week. So on the x-axis, basically of each of these plots, each point corresponds to 1 week in 2020. So we look both at countrywide, but also specific regions. Namely, we look at 5 metropolitan counties, which we mark on the map below the legend there. In terms of the data traffic patterns, we noted that the evolution at the UK level, so the countrywide, is similar to that at the metropolitan county, for more or less for the 5 different counties we captured. In particular, the data traffic volume dropped by 20% or more, while the number of downlink active users also decreased together with the cell resource utilization, which makes sense. Maybe unintuitively, however, the throughput also dropped by 10%, and we put that likely because of application throttling, but this is just conjecture. We also see that London actually made a discordant note from the rest of the areas, with a steep decrease in the number of users, and both in the uplink and the downlink data volumes. So we confirm later with our analysis that this is likely due to the temporary 10% relocation of London residents who did not remain actually in their homes after lockdown. So next slide, please. Right, so we not only looked at all this analysis based broken down per metropolitan county, so at this geographic units, but also we looked at the analysis on geodemographic clusters. And I'm not sure how much time I have, but I'll quickly explain what these are. So every 10 years, the UK runs a census, and with the data from the census, they actually classify output areas in different clusters. They call them output clusters. And what you see here in the legend, they are the largest clusters that we can use. And you see them in the plot, in the map in the left side. You actually see how all these clusters map to different geographic areas. So then instead of looking in the limits of a specific area, we actually looked at this geodemographic and tried to understand how the performance of the network maps with these geodemographic clusters. So what we immediately see here, the first thing that jumps in our faces is the discordant that London makes with the rest of the different geographic clusters. So the blue one is the cosmopolitans. They usually map in central London areas. And as you will see in the next slide, we actually found that a lot of the people who living in central areas in London are going to move away. As I said before in the previous slides, or in the initial slide with the main takeaways, the voice traffic actually surged we actually found 140% in the value in terms of the increase that we in the total volume. However, this also put a bit of a strain on the network that actually interconnects the different operators. That was quickly fixed, and this was basically showing the rapid response of the network operators and the service providers, restoring the quality of the service. So next slide. So finally, I show you the well-promised temporary relocation of the residents from London. So in this matrix, what you have on each of the columns are different days, and the rows represent different cities within the greater region of London, within inner London. So you see how people from inner London moved to other cities around London. So you immediately, the first 2 weeks, you observe the weekend patterns, which disappear. Now, if you focus only on the line of inner London, you see that the color goes slightly towards a lighter blue, which basically means that 10%, we see a decrease of 10% in the number of inner London residents who actually are present within inner London after week 13 of the lockdown. And then we see that just prior to the actual lockdown being imposed on the 23rd, which was the Monday, you actually see a bunch of movement happening that corresponds to people moving, residents moving from inner London to, for example, areas like Hampshire or Kent, just on the weekend before the 23rd. So next slide. Right, this is just an update. As you probably know and you've seen the news, there is a new lockdown imposed now in the UK. So they started with like tiered lockdowns. Now they've entered like a full lockdown, but milder than before in March. So we looked only at how mobility changed across these last 9 months. Next slide, please. So only if you think about I'm not sure how well you can read this. It's not the best, the easiest to read. But this is just the evolution in gyration. The upper part is just the same bar plot that you saw initially, but now it goes until the end of September, if I'm not mistaken. So you do see that across the summer, this social distancing kind of diminished considerably. And now as we go into the second lockdown, the gyration starts to decrease and probably will go down to the levels that we see in the first lockdown. You check different areas as well at the month, aggregated per month, and this is what you see in the bottom part. So, the steep decrease in March, and then a slight relaxation of, that goes step by step in the months towards summer. All the rest that looks normal sort of in terms of mobility of people, and then we go to September and we see this decrease, and we're analyzing this to see how this affects the new lockdown affects the mobility of people. So I think this is it for me.
Thank you very much. So I think this is like my two high-level takeaway messages is that first, the situation looks slightly different on mobile networks than maybe for other networks. And also that this is a lot of interesting data about people mobility. That's very helpful as well. You mentioned very briefly that also mobile operators had to react and extend their capacity, but I guess it's you cannot put up new base stations just now, right? So do you have any insights what they did and how that worked?
They did deploy 5G, and I confirmed it does not cause COVID. No, that's a joke. That's a bad joke. They were deploying actually 5G across these months. And they were, especially in London, they were extending, and probably you've seen the news, the press releases that O2 made. They were deploying capacity, especially within London, around the areas of outer London. They focused. The issues they had in terms of capacity were more towards the interconnects for voice traffic. That was short-lived in March, like the 23rd, immediately. So the first week before lockdown and the week after lockdown. So it was the effect of a natural disaster that you observe when people just pick up the phones and they start calling. And you see that even if, in huge, in earthquakes or natural disasters, we saw exactly the same pattern. And this matched that. But actually what was interesting was that even after the week after, immediately after the lockdown, the voice traffic stayed, at basically was constant with an increase of about 50% compared to February. So it kind of remained at very high levels compared to before the pandemic.
We have Yari in the queue.
Yes, thank you for this. This was really interesting data and really interesting presentation. I think you liked that we went into the details behind the big numbers, like the demographics and people moving back and forth between places. And just wanted to comment on one thing that we at Ericsson had, or some of our colleagues have measured traffic in different countries, and they saw a lot of variation. One of the possible reasons for that variation is how much sort of fixed network capacity or users there are in a country. So, for instance, in India, they rely quite a lot on the mobile networks. So during the pandemic, traffic there grew a lot in those networks. And I wonder if that might be an additional detail behind the big numbers that one should perhaps, or somebody should look at, whether people have their fixed networks and whether that affects how much traffic there are sending or not. If they move, let's say, from their home to the summer cottage, they might not have the same connectivity there. So there might be more factors to look at than I understand. I don't know if you have any of this data on your data set, but
so I think it would be great, and this is something that we've been struggling with quite a lot, to try to understand the why behind what we see, right? So one immediate assumption is that, okay, the traffic decreased in terms of mobile network usage, so the waterbed effect should have been seen for the fixed traffic, for the fixed network traffic. However, we don't have that sort of information to check for the same users. We're not we didn't know how to verify this. So we left it at, the conjecture level. So we could only assume that that's what happened. But then it would be very interesting to be able to put together, for example, an ISP in the UK with a mobile operator and check, in the same demographics, how, if actually this waterbed actually happened, the 20% drop and the increase, proportional increase in the ISP traffic.
Right. Okay, thank you.
Sure, thank you.
Thanks. If we don't have any more questions right now, we would go into a break. Given we're already behind time when we have some more talks, I first of all need to ask everybody who's presenting next to speed up a little bit and be as brief as possible, because we also want to have some time for presentation left, for discussion left. But I would suggest that we really only go quickly into a 5-minute break so everybody can grab a glass of water or coffee or whatever, and then we restart with the next presentation. And Stephen says in the chat that you, of course, can keep discussing in the chat. And we will also monitor the chat and try to make sure that points are captured in the report. Okay, see you in 5 minutes. Okay, hard to tell if everybody's back. I'm here. 5 minutes are over. So we will simply kind of start again. I noticed that I actually didn't introduce myself, and WebEx is nicely hiding my name. So just for the record, my name is Mia Kühlewind. I'm an IAB member. And I would also like to quickly introduce those people from the IAB who helped putting this program together and reviewing the papers. That Stephen Farrell, who has been already talking, and you've seen his video at the beginning. There's also Yari Akko, which has also asked some questions already. And then there was also Ben Campbell, who is here today, but hasn't been active yet. So you're the next one to ask a question. And then we have also Colin Jennings here from the IAB, who will share the session tomorrow, but he can introduce himself tomorrow, I guess. Okay, with that, oh, sorry, I forgot Colin. Colin Perkins was also helping reviewing papers, who's the IETF chair. Sorry. And with that, I believe, because Jason just turned his video on, you're presenting perfect. So then go ahead.
Yep, thanks. So thank you. My name is Jason Livingood. I'm an engineer at Comcast and IFT in the United States. And I'll be presenting today with my colleague Nick Feenstra from the University of Chicago. Next slide, please. And we'll certainly go through this quickly. These are the folks that we are collaborating with. Next slide. So the high level here is that we were interested in COVID-19 effects, specifically 311. Looking at both long-term trends in interconnect data and some near-term ISP observations. And so the primary data source that you could sort of put in the general bucket of
Nick, I think you're not muted. Thanks.
So the primary data source, which Nick will go into momentarily, is from the Interconnection Measurement Program. It was kicked off in 2016 and is still running today. And essentially this is comprised of sampled netflow data or IPFix data for all of the interconnect interfaces across multiple ISPs. And so, timestamp the region where the interconnect is, and then anonymous peer IDs. So the data set that Nick and his team have doesn't identify a specific peer name, just a random anonymous identifier. Of course, access ISP, total bytes, ingress and egress, and capacity. So Nick's going to dive into this, and then we'll come back to me. Nick, next slide. Nick, you might be on mute. Go ahead. Still on mute.
Nick sent email saying he might have to pop into in and out of some other meeting as well.
He's here, and he seems to be talking, but we can't hear him.
Got it. All right. Well, I will jump into this then, and we'll come back to him in a second. So the key findings here is that I think similar with the other presentations that we saw an enormous increase in utilization in a very short period of time. And at the same time, new capacity was added in a very brief period as well. So we see, of course, a steady increase in capacity in the Interconnect Measurement Program of capacity, particularly from mid-2018. But beginning with COVID, we saw nearly twice the rate of 2019 additions. So in a very short period of time, all of these interconnect interfaces were having a lot of new capacity added. That growth continued, not just in this initial first quarter, end of first quarter timeframe, but through the second and third quarter. So it has continued, and let's see, if we go to the next slide, we can see a bit more. So Nick, are you available now? I see you've stopped talking. Are you available to speak to this, or should we come back to it in a second?
I'm here.
Go ahead, hit the slide if you could, and then I'll do the
Okay.
Nick, you seem to be muted.
Can you hear me now? Okay, good. So in this slide, we're basically looking at peer link utilization, in particular, how much traffic goes across the links from a particular ISP in the upstream or downstream direction, and then comparing that to between two periods, January 1st, 2020, and then September 1st, 2020. And what you can see basically on the diagonal is that the diagonal shows basically that would be like equal ratios up and down respectively from those two time periods. If it's above the line, we basically would see an increase, and if it's below the line, we'd see a decrease. And each point is a peer. And so what you can see is basically that traffic volumes and ratios change significantly between those two time periods for specific peers. This is data that we looked at both from the ISP perspective as well as from the interconnection measurement project. You can go to the next slide.
Great. So just to wrap up, in addition to the long-term IMP data set that Nick analyzed, just some individual observations looking at all of the detailed Comcast interconnect data. We definitely saw about a third increase in that March-April timeframe, and it happened, as other presenters said, really in a matter of days. So that was a year's worth of growth in a few days, which was astounding. When we look at our access network to date, certainly it peaked, in that March-April timeframe, went down due to seasonality in the summertime, has come back up now with return to school in the August-September timeframe. But over that period of time, we've seen downstream consumption or usage in the access network up about 13% and upstream up about 36%, largely driven by things like video conferencing. We saw a huge increase in the amount of access network augments, so 400+% in many weeks, which was big. 500+ augments to our core network. Those are primarily at the edge. So think of the interconnect links. We've done through this period as well, this isn't really interconnect related, but about 700 to 800,000 tests per day to cable modems in the network, just to measure QoE in addition to traditional capacity measurements. And notably, so within our interconnect link types, one of them is settlement-free interconnect. And typically those would grow at about 15% a year, so a little bit slower than the norm, but those went up 37% over this period. And some of the notable per partner ones were interesting. So it seemed like our interconnect growth were heavily driven by specific partners. So it wasn't across the board that everyone was increasing, but that particular transit networks, content delivery networks, or web conferencing providers just saw amazing growth. So in one example, one peer more than doubled 115%, basically in 4 to 7 days in a week's period. And then we saw other platforms up 3,900%, which is just mind-blowing. And more of the norm was 1 to 200%, which is crazy to say. So that is it. And for more information on the next slide, you can obviously click on the paper. There are more insights there, and we're happy to take questions later on. Thank you.
Thanks. As you were mentioning the speed test here and QoE, you increased your test volume here. Did you also notice actually more QoE problems? And do you have any kind of data or like rough numbers for that?
Yeah, I haven't, we didn't share that in this paper, but there's another paper, I'll post it in the chat, paste it in the chat, excuse me. And so it was kind of good timing that we had this test come out in early February, right before the pandemic. So we had a little bit of beforehand volume. And what we ended up seeing is certainly, in some cases in that early time frame, an increase in latency, a decrease in the percent of advertised of speed. But in all cases, we still were above 100% of advertised. So we had that extra buffer, as one of the earlier presentations said, of capacity, and it ended up getting consumed we ran close to where we thought that was like the danger zone, and then very quickly added capacity back up to recreate that buffer, if you will. So we felt pretty good about that, and that correlates with a lot of data sources like Ripe Atlas and their latency changes in their data and so on. So it seemed to work out well, we felt lucky that we had that extra provisioned capacity, certainly it makes my job easier and our team's job easier with our finance folks who have always said, why do we maintain all this extra capacity if it's not being used? Well, it just got used very quickly, and that's why we have it. So it was interesting.
So did you mainly measure throughput and delay, or did you also try to look in like more application metrics which are closer to application performance?
So our test did not look at application-specific metrics. They looked at upstream and downstream throughput, latency by itself, and then latency under load. And I'll just give a quick preview on latency under load. It's a thing, and it was a big thing in the pandemic, both on the LAN side, which would primarily be the Wi-Fi LAN, and then on the upstream network link. And we actually had, just through an accident of where software releases ended up being, one particular device model, one made by one manufacturer, another a different manufacturer, different chipsets in them, so slightly different software. On one of these, we had basically an AQM turned on, and then the other, it wasn't quite ready yet. So for a window of time, we had an exact same exact same model, slightly different chipsets and manufacturers, one with AQM, one without AQM, with very interesting differences of latency under load. So that's in the process of getting written up now to share more information, but it's a big deal. And I think there's a lot more to be done to study the Wi-Fi LAN side of things. We've seen a lot of significant issues there.
Very interesting. We have Jared in the queue.
Hi, Jason. I'm curious. I know a lot of people either upgraded their data, kind of upgraded their speeds, and also actually, I know several people who entirely switched technologies during, as a result of cable having much higher speeds. I'm curious what how much of this traffic was just organic traffic growth, and how much of it was additional subscriber base. If you can comment on that. If you can't, I understand, but I'm just curious.
Yeah, I mean, I haven't looked too specifically, but off the cuff, I would say most of it is from existing subscribers, just because the subscriber base is so large. It was like 24 or 5 million homes before the pandemic. We have added a significant number of new customers, particularly with what's called our Internet Essentials tier, which is a 25 megs down, 3 megs up for $9.99 a month for low-income folks, and that's added a huge number of people. But even within the existing subscriber base, lots of people upgrading because they're all working from home. Much like me, I went to a gig.
Okay, we have one more question in the chat. I'm not sure, Ben, if you want to join and ask a question, or if you should just move the discussion to the chat and move on. Maybe let's do that. Okay, and then next we have David Clark, and we will look a little bit deeper into congestion problems.
Hi there. I'll try to be quick on this because I understand we're running late. This is a different perspective on some of the same stuff that Jason and Nick were talking about. Go to the next slide. Back around 2016, CADA and at UCSD at MIT started measuring congestion on links, because at the time there were all these disputes between the big ISPs and the big content providers. There's a lot of congestion on the transit links. Now this is outside measurement. Jason's talking about data he has. We can't get the data from the routers. We have to probe, and what we're doing here is I'll very quickly try to explain the background. We're basically every 5 minutes we probe a link. We send a TTL expired packet near side, far side, and what we look for is episodes of elevated latency, which tells us there's queuing on the link. So it's an indirect measure of congestion. And we're probing every link we can identify. The data I'm going to show you here is from Comcast. We have data from most of the large American ISPs and some overseas. Just so you see what the data looks like, go to the next slide. This is a picture from the bad old days when there was a lot of congestion on transit links because of disputes with Netflix. And this is the signature we look for, a daily pattern of elevated latency, which tells us that there's probably congestion. There are lots of reasons why you could see elevated latency, link changes or route changes or traffic management. So we look for this recurring pattern to give us confidence we're actually finding congestion. So we can look at this data and try to decide whether we've seen anything interesting when the pandemic started, because we've been collecting this stuff for several years. So go to the next slide. This is a picture from Comcast, and notice, just for fun, it goes all the way back to 2016. And what we're doing is we look at every link we can identify. We don't necessarily find all the links, but every link we can identify. In this case, it's Comcast, peer, major content provider, cloud provider, transit providers. I'm not plotting here their customers. And I took an arbitrary measure, which is the link congested for more than a half hour a day? And I just add up the total number of links that are congested. I'm just lumping them all in one big basket. And so what you see is, around 2017, 2018, you get these huge spikes, which is where a lot of content providers were dumping traffic onto congested links, and then it goes away. And you see 2019 is pretty flat, and then you look at 2020, and what you can see, I'm going to drill down, but what you can see is in the first few months of 2020, you can see that more links are congested, and then it sort of goes away again. And then maybe there's something interesting right at the very end there, and we'll go look at that. Now, this is, of course, just looking at every link, but we can, of course, identify the autonomous system that's on the other side of every link. And Nick and Jason have to be a little circumspect, but we're probing from outside, so I can name names. So look at the next slide. What I've plotted here is the interconnection partners that contributed to congestion. And the first thing we need to get out of the way, if you look on the right side, there's this huge lump. Now let me explain what I'm plotting here. I've organized the data into 2-week baskets. And what I count up now for each interconnected party is the number of congested day links that there are in 2 weeks. So if you found a number 14, if you look over on the right-hand side there, 14 says, on the average, one link was congested every day because of 14 days in 2 weeks. And that huge lump on the right-hand side is Akamai. And you might say, well, what's wrong with Akamai? Well, the thing you got to remember in this context is that Akamai has well over 50 links. The reason I don't know exactly is that we try to identify link aggregate groups, but we don't always necessarily quite get that right. So basically what you're seeing here is that there were 2 or 3 links from an Akamai server into Comcast that were congested. And in fact, we did confirm that. And you notice it went up and then it went down. But if you, but actually it doesn't surprise me that there might be technical reasons why 2 or 3 links couldn't be upgraded. Obviously, since they have 40 or 50, there's not a business issue here. If you look around March, 2020-03, you see various things spike up. You see Cloudflare spike up, and you see Telenet, and then they go down again, which is exactly what we saw from other data. Now, the important thing is Jason can tell you exactly about link capacity. I can't measure link capacity, but when he talks about link capacity, we don't know whether the link went from 30% loaded to 70% loaded, or it went from 60% loaded to, it was trying to get to 110% loaded. What we find here is actual congestion. And when I look at this picture and I look off into January, September, October, up to the beginning of November, you see little spikes there. But in general, what I think you see is exactly what people are saying, which is bits of congestion occurred here and there, and people put in extra capacity. Just for the fun, look at the next picture. I won't dwell on this. These pictures are all in the paper we sent in. Yeah, go skip over the discussion. I already said that. And again, I went back to 2016 just so you could see who was congested back in the period when there were all these disputes. And what you see is back then, the congestion were on YouTube links, Tata links, NTT links. So the congestion moves from place to place depending on what the business issues are more than the technical issues. So there are graphs for the other ISPs, major ISPs, in the paper we sent in. In general, the story is about the same. You see some congestion occurring in March, April timeframe, and then it goes away. And in general, what people are saying is, yeah, we put in extra capacity. So what? Go ahead. Next slide. I think that's all I had. Yeah, that's all I say. If you want to see some more pictures, go look at the paper. But as I said, for the US, they more or less look the same. So I'm done.
Thanks a lot. I specifically really like this methodology that you actually look at congestion and not only bandwidth. That's really helpful. Any questions? Then I'm sure there's more on the chat. Thank you for now. We might pick this up later again.
Sure.
And let's go to the next talk. Next, we have Ricky looking a little bit closer at the interconnect to the cloud.
Yep. Hi, everyone. I'm Ricky from CADA. So this project, we are measuring, instead of measuring performance from the edge, we do another way around to measure performance from the cloud to SS network. Next slide, please. So in this project, which is one of the NSF funded project for, in particular for setting up measurement for measuring the impact of COVID. Actually, we built a system called CLAPS to set up many VMs, mainly in US regions, to perform throughput measurement to a number of speed test servers. We use 3 types of servers: Ookla, Comcast, and MLab NDT servers to measure the throughput in both directions, and see how the cloud is performing during the pandemic. We start our measurement in May, so we kind of measuring the aftermath of the pandemic effect and see how's the performance going while the people start moving again, and also like some re-lockdown events happen during the pandemic. So here we are going to show some very preliminary results that we have right now. So next slide, please. So actually find that the cloud is not as good as we thought. We definitely see evidence of congestion, not only to small network, but also can find congestion events in between cloud regions and like big access network like COS. We can definitely see very significant throughput fluctuation. It's kind of like a diurnal pattern recurring every day that we have the throughput drops in a certain period of time. This is a download direction, which means it is from the ISP to the cloud, which probably caused by impact to like video conferencing application, like Google, could be like Google Hangout in this traffic direction. So next one, please. For small ISP, sometimes it could be even worse. So these two data shows one view of data of from AWS North Cal regions to 2 small regional ISP. One in North Colorado area, and the other one served South Colorado area, and the other one served North Texas area. So those service area are more suburban area, and we can see that the upload direction means that from the cloud to the ISP is mainly served the like video content and also download activities. Definitely, we can see suffering bandwidth degradation, and user is kind of suffering during like evening time. And the other one actually we show a persistent low throughput except those midnight off-peak hours during this week. So next one, please. So apart from like daily variation, we also have a very high-level view of the data between months. So we pick the first week of each month to see the median download throughput between some certain cloud region and ISP, and we can find some downtrend in the certain cloud regions between cloud regions and certain ISPs. Like the left one shows from the spectrum to Azure Central Central One region, and we can see that the throughput from like 6 to 7 spectrum servers actually decrease over time. And we also can see like a slight decrease from Comcast server to AWS, Ohio region between 3 months, over 3 months time. So next one. So apart from access network, we also take a look on the educational network because everyone moved from like in-person learning to distant learning. We also observe a downtrend in a certain area of cloud regions. We cover 3 different universities in one of the GCP regions, which is East Coast. Although we saw some evidence that there's less user in the campus, but we find that the throughput could show some downtrend during these 3 months. We investigate, try to investigate on this, whether there's a route change or they may have used more distant learning tool that may cause throughput degradation. So next one. So to summary, actually, we use throughput measurement or speed test measurement running from the cloud to different ISP, and we find that actually the cloud is still suffering some congestion events. We show some evidence of end-to-end throughput degradation because of like end user or last mile link is mainly because of the performance network between 2 big parties in the network. And we observe some downtrend in throughput in the post-lockdown period. We have the data until October, and we will keep working on the analysis and see whether the downtrend continues or it comes back some later. We make the data publicly available. It is now, we're still working on it now, and we will put it online later. So in our next step, we will also happy to work with other people on correlating different data sets and see whether finding CSM finding with other data source, and we may have physical and efficient tests in the later in the future. Thanks.
Thank you. Thank you very much. I think Nick just answered my question in the chat that I wanted to ask now, because my question would have been, have you looked at latency as well or only at throughput? And Nick said, and they have a similar paper where they provide also some insights into latency, and they also see effects on latency. Can you confirm that, or did you not look at that?
Oh, no, we have not looked into that.
Okay. Yeah, but definitely, I think one piece of the puzzle to look at. Thank you. Are there any further questions? Okay, we have two more brief presentations. We now go into the part where we talk about last mile congestion. We get some data from Japan, and then we also get some more general data from RIPE Atlas, also looking at latency actually. So next we have Kenjiro.
Yes.
Hopefully, yes. Let me find your slides. I believe those ones. Yeah, that looks good.
Yeah, this one. Okay. So I'm going to talk about broadband traffic in Japan, which is not so different from the the other countries. So next, please. So this graph shows the the IIJ's broadband traffic since 2015. So the green line is a download. So until last year we had a steady growth, and in this year we have a surge. So we had the first wave in February, and then in April May timeframe we had state of emergency, and then we had second wave in the summer. So we can see in the graph, the increase of the traffic during the state of emergency, and it goes down and it goes up again. So but if we look at the overall trend, it seems not that far from the original growth curve. So next, please. So these are details from February to June, and these are summarized in the next slide. Next slide, please. So what we observed is, as Oliver said at the first talk, the weekday traffic became similar to weekend traffic under state of emergency. So the left plot is weekday, and the right plot is weekend. And the blue one is before, and red one is under the state of emergency, and the green one is after the state of emergency. So for weekday traffic, so during the state of emergency, the daytime traffic increased a lot, and after the state of the emergency, it goes down again. And during the state of emergency, the traffic looked very similar to the weekend as people stayed home. And next, please. And this one looks at the distribution of the traffic usage per user. So it basically plots the upper plot is for upload, and the lower plot is for download. So it's an evolution of the distribution for the last 10 years. So if we look at the longer term trend, so this year's increase, this is measured in June, so after the state of emergency. So if we look at the evolution, this year the evolution is bigger than previous one, but it's also not so far from the previous trend. If we look at in the semi-log scale, so the download volume, for example, evolved for the last 10 years by 2 orders of magnitude. So 10 to the 9th is 1 gigabytes per day. So these days, if we look at the mode, people download 3 gigabytes per day. Okay, next slide, please. So in summary, so the overall macro level impact to the broadband traffic is not so big. So the traffic increased during the work hours, but it was still under the capacity. And after the state of the emergency was lifted, it's slowly coming back to the original growth curve. And we have many reports, talking about the minor issues, mostly with legacy infrastructure and the equipment. So in Japan, the broadband boom started 20 years ago. So we do have legacy equipment like PPPoE. Roman will talk about in the next talk, and VDSL in apartments and old Wi-Fi at home. And we had some good luck because we didn't have any real lockdown in Japan. And we are still, are you still hearing me? Okay. And we are doing okay so far. And also, the Olympic game was scheduled this past summer. So the many infra capacity upgrade was scheduled early this year. So many upgrades are already scheduled this year. And also for preparing Olympics, many big companies, industries push for remote work. So people are prepared. So these are observations from IIJ services, but we have similar reports from other Japanese ISPs. That's all.
Yeah, and here I would suggest we just go on to the next talk immediately and dive a little bit deeper into the latency measurements. Yes, and now I need to find that one. This one.
Can you hear me?
Yes, we can hear you.
Cool.
But not sure what happened to your slides. This one.
Would be very quick.
There they are.
Okay, so and that's great because Kenjiro brought all the background. So in this work, we're looking at the last mile latency, and you can go to the next slide. And so what we've done is we took a ripe at last trace route, and we tried to estimate the queuing delay for the last mile in the trace route. So we just look for what is the last private IP we see and the first public IP, and we're going to say this is the last mile. Then we monitor those delays over time, and for a lot of ASCs that host ripe atlas probes. We are not really interested in the delay for just like one probe, so we try to aggregate those results per AS, hoping to see if a common pattern could emerge. And this is what is shown in those figures here. So the x-axis here is the time of the day. It's all UTC time because those networks are in different countries. And the y-axis is the aggregated queuing delay. And the colors of the curve shows different measurement periods. So the blue, orange, and green are in 2019, before COVID-19. And the red one is during April 2020, so when a lot of networks were impacted. So I guess it's not a big surprise. We see increase in latency for the last mile. What all these networks have in common is we see increased delay during the day. So all of these figures have a peak in the evening. So the top left one is in Germany. So the UTC is more or less the time in Germany. The bottom one are in North America. So the peak is on the left of the figure, and the top right one is in Japan. So they usually all have like a peak in the evening, but during COVID-19, we can see the latency increase during daytime. I would say the two bottom one just have like a slight increase. The most significant one here is in Japan. So the top right one, where we've seen very severe last mile congestion. And in our paper. So we just restate what Kenjiro said, like there is some problem with the legacy infrastructure. So using those results, we could point out that the problem were coming from there. And so next slide. In our paper, we try to collate those results, those latency measure with throughput. So in the paper, we use CDN data, but here I've redone some of the experiments using MLab and DT data. And we found that the throughput drops are very correlated with the delay increase we've seen. So on the left, you have the throughput for NTT OCN. Here, the measurement period are a bit different. This is to match what Kenjiro said. Like in Japan, we had a state of emergency. So the blue one is before that. The orange one is during the state of emergency, and the green one is after the first wave. So we can see again in the throughput that we had throughput drop during daytime compared to what we had at the beginning of the year. And like Kenjiro said again, we see that after the first wave, we have a bit higher throughput. And our guess is that this is thanks to the upgrade that was planned for the Tokyo Olympic. And next slide. So that's all the result I have here. So we found overall the number of congested network we see using Atlas is in fact quite small. We've observed only about 10% of the ASN we monitor with Atlas that usually have last mile congestion problem before COVID-19, and this increased by 55%. So in Japan, we dig a bit more in the result and found that one of the cause was the legacy network, usually accessed via PPPoE. We have other results I haven't shown here, but using MLab or the CDN data, we found that the mobile network is unaffected. And that those two URLs, so the first one is the paper with some more results. And the second one is actually is completely unrelated. It's some measurement we've done where we look a bit further in the trace routes. We are not looking only at the last mile, but we are looking at delay between two networks. So it's a bit more similar to what David Clark have presented before. That's a dashboard we've done during the hackathon, a RIPE hackathon. But well, that brings something else for our discussion if people want to discuss that. Thank you. That's all I have.
Thanks a lot. We can check if we have any questions. There was like one question about what's the unit of the y-axis on the previous slide.
That's in millisecond. Yeah, and
okay.
Those values are very small. In the paper we show that because it's aggregated across like all the probes. So it's the median. Sorry, I didn't explain very well, but it's the median value we observe across all the probes in that network. So that means that about 50% of the probes have more than that value. It's a bit hard to plot. Like it's better to see the whole distribution.
Yeah, thanks. I mean, there's more data in the paper.
Yeah.
So basically, that's the end of the presentations, and we only have little time left. But at least I would like to thank everybody who presented, because even so I read the papers, seeing everything together, putting like the data somehow in context, I think was very helpful. My big takeaway really is that it's not enough to just like look at one angle. We need like all the different data to actually understand what's going on. The other point is that I think we realized during the session that we actually do need more data, especially about quality of service or quality of experience for specific users, for specific applications, for specific service providers. That's all different. There might be regional differences that we didn't have enough data on. With that, I will just quickly turn back to my own slide set. And we can stare at this slide for one more minute. I think I already we already tagged it that we potentially need more measurements, but we need also more digging. But I want to open the question to everybody. Where do you see problems? Where should we look deeper? What else should we measure? What's missing? What's actually normal? Do we understand well what has changed? Do we understand well what the requirements from the society are? What the needed quality of performance or quality of experience is? What are the differences? And then also maybe this is then sliding a little bit into the session tomorrow. We should think about what we want to discuss tomorrow, and did we actually manage it well, or was it just luck? So the floor is open. We have Brian in the queue.
Let me put the camera on. Hello, can you hear me?
And we can hear you. I should say the session is on Wednesday and not tomorrow. So
yes. That's the first point. Yeah, so I think one of the things that struck me from looking at all of these talks, which were great, thank you to all the presenters, by the way, was there are a lot of sort of common bits, right? Like, so, hey, the internet kind of worked, at least if you look at the core. And a lot of expected bits. I guess if you had said and looked at the Japanese home broadband infrastructure 2 years ago and said, by the way, we're going to need to triple the load on this network in 3 weeks. I think actually, if you look at the investments that were made for the Olympics, you can see that people knew that that's where the problem was. The one thing that kind of jumped out at me from some of the talks about the capacity adds is that it was actually possible to add capacity at there was Comcast had one that went up by a factor of 40 during the pandemic, that it was possible to actually do that. I'd like to, so I think Jason made a comment that, the bureaucracy kind of got out of the way, which is one thing, but it'd be interesting to look and see if there are any remaining gaps in how fast it takes out to roll out the physical infrastructure. And it seems like at the interconnection points, there isn't any remaining sort of barrier to physical infrastructure, but that might be something that we can't actually answer with measurement, is like, what would the next big thing we'd have to do in terms of capacity expansion be, and is that a technical blocker or a non-technical blocker? I guess
as you're saying this, my question would also be if we need another 40 times capacity, is it still possible now, or are we now at the end?
Would we need it? Right, because you can see that over time the previous stuff was clearly business limited, right? Because if you can do it twice as fast or 39 times as fast as you were before, well, then you just didn't need it before. But yeah, I'd like to dig a little bit more into that. Again, that's probably also a tomorrow question. But thanks.
Yeah, actually, my assumption was that a lot of people just took the expansion that was planned somehow and did it earlier, right? So there was already some kind of planning, and there was already maybe right things aligned, right? So not sure that's possible again very quickly like this, but that's also something we should understand tomorrow, maybe.
And there's one of the talks that said, hey, we carry 30% additional capacity for 30% year-on-year increase, and we also needed 30% additional capacity. So that feels like luck to me, but it'd be good to sort of take a more reasoned approach to that.
Yeah, definitely tomorrow. We had somebody else on the queue, but now I can't see it anymore.
You already?
No, Matt first.
I was wondering how well calibrated the data is about our background organic growth. Back when I was really active in the IETF, it was typically 13-month doubling time. And now I'm hearing 30% per year. How well is that? How stable is that? How well known is it? How well documented is it? And one of the approaches that I know was used in the past when there was big surges was taking the point of view that an unexpected load is sort of equivalent to a failure, and you have to reserve at least double capacity in order to be able to deal with failures, and being allowed to eat into that reserve to deal with crises helps a lot.
Yeah, so like, do we actually still have this reserve, right, for failures? That's another question. Yeah. Next in the queue is Yari.
Yeah, so trying to answer a couple of the questions or propose some partial answers at least. So I think your initial conclusion that we need more measurements and need to look at things like holistically, not just from one particular angle. I think that's exactly right. And some areas where I don't think we have enough is the quality of experience, also application-based measurements. How much do we know about, conferencing platforms and such? And so everything that we saw today was really great, and amazed that we have had those numbers, but it would be even better to have more. By the way, I in my paper I had some material on quality of experience, and like Ericsson had asked people around the world like how did they feel about the situation and so on. So I'll post a link to that. But that's a sort of a feeble attempt or simple thing. I think we need much more. The other thing that, like you were asking this about luck or well managed, it's kind of like what is your expectation on the risk level that you want to handle? Like, can we do a pandemic and I don't know, a meteorite hit that takes down 10% of the current infrastructure? You know, in some sense, we were lucky because we did like it was a big change in the society, but you know, everything was sort of retained and nothing sort of initially broke down and so on. So, but do you want to build for that? Do you want to pay for that? That I think is the question mark. But one of the things that the Ericsson research actually did observe is that at least for the moment, the consumers are really interested in reliability and resilience of the networking that they use or enjoy or purchase. So at the moment, at least everybody is interested in, like, are you going to be able to deliver this thing for me going forward? Hopefully that can be, or that sentiment can stay for a longer period of time.
Yes, totally agree. Let's take Oliver Hofeld's question or comment.
So I actually want to make a comment that goes a little bit into Brian's direction. So to me, the question is like, on what level of granularity are we talking? Most of the results, also the results that we have shared, are at the granularity of we take the ISP or the IXP as a whole. And this level can be, or this picture can completely change if you look into individual users, individual peering links, and so on. And of course, we have seen these cases where, smaller enterprises were kind of like not really planning for this pandemic to happen. And then if they send all of their employees to home office, then of course the small pipe that they have purchased, it went from like a medium utilization to like a really high utilization. So of course they can have like this can really have like an effect on them. But if you look at if you do a statistical analysis on like the operator or the network as a whole with like a large set of peering links, then we see like a kind of a different perspective for the majority of the cases. So I guess that's like one thing to discuss for the Wednesday session is like the level of granularity and how like how deep should we dig into like individual users that really suffered, individual links that went to full utilization, so these kind of things.
Yeah, definitely. I mean, like that was also one thing is actually understanding what the problems are, understanding all the details, understanding who suffers. But then the other thing is actually the big picture, right? Is it the architecture? Is it the technology where the limitations are, or is it a business question? I think that's also a good point where we hopefully come to some insights at the end of the workshop. I still have Cullen in the queue.
Yeah, I just want to
we
basically wrap
out
anyway.
of time. Okay, perfect.
Yeah, I don't want to comment on this. I just want to tell people, if you would like a less than 7 minutes or less lightning talk slot on Wednesday to talk about one of the operational issues, send slides or a request either to me, fluffy@cisco.com, or to, and I'll put my email in the chat, or to the program committee list. And let's see if we can have some more time for discussion of this and that stuff on Wednesday.
Yeah, and I have a request. I would like to ask people to actually go to the note-taking pad that we have and add comments there on things that you think we should measure, we should do, we should care about, so we don't all forget about it immediately, and we can look at that on Wednesday again. Yeah, and with that, we're at the end of this session. Thanks everybody for joining. Thanks everybody for presenting. Thanks everybody for comments. We didn't have as much time for discussions as I was hoping for, but it was also a little bit expected, to be honest. But I hope you all enjoyed the session. I did a lot, and I think we're now well prepared to have discussions on Wednesday. Any last words from anybody else from the program committee? Okay, then same time on Wednesday, same link. Thank you, everybody, and goodbye.
Thank you, Mirja, and all the organizers.
Thank you.